the Aerospace Systems Directorate. We are the Rocket Propulsion Division. Our mission, the last 60 years, develop and transition advanced rocket propulsion technologies to the Air Force and the nation. Nearly every space and missile system this nation has ever flown finds its roots on this desert floor. It was 1947 that we outgrew our facilities at Wright-Patterson Air Force Base, Ohio. Technological advancement forced us to a much-needed remote and safe location. Our new home, the Mojave Desert. Specifically, Edwards Air Force Base, California. You've heard the term, it's not rocket science. Well, this is rocket science. This is the home of the real rocket scientist. We have over 400 government civilians, military, and contractors on site conducting basic research, exploratory and advanced development, and testing of operational or developmental systems. Our military, active duty, and reservists bring with them extensive field experience in ICBMs, space launch, and program management. Our machine shop is the top in the Air Force. Their unique skill set enables them to build highly specialized test equipment needed to test the new technologies we develop. Since 1947, we have grown to be a $3 billion national asset with 135 major laboratory and engineering facilities and 30 major active test stands. You couldn't do that in Ohio. The Mojave Desert. There isn't a better place to do rocket science. In our bench scale labs, we synthesize and investigate novel new ingredients and materials. We can simulate space operations in our altitude facilities handling nanonewton spacecraft thrusters or 50,000-pound upper stage engines. Our sea-level stands can handle ballistic missile boosters and liquid engines up to 2.5 million pounds thrust. AFRL covers 65 square miles of the Mojave Desert, nearly the size of Washington, D.C. This is beneficial to you because around the country, population growth, encroachment, and increased environmental constraints have driven many commercial and government facilities to curtail, if not close down, their ability to conduct rocket propulsion testing. Even after 60 years, despite increasingly stringent environmental regulations, we're still able to conduct the full range and scope of rocket propulsion technology developments. With a budget of approximately $80 million, we conduct an impressive array of rocket research, both in-house and with our industry partners. In-house, we conduct basic and exploratory research in combustion physics, ingredient synthesis, and propellant formulation supporting our liquid and solid rocket and spacecraft thruster developments. Our in-house liquid rocket engine work covers both basic and exploratory research. We investigate novel, injector, thermal management, fuels, and combustion stability technologies. We have one-of-a-kind capability to study injector physics on combustion stability in both cold flow and hot fire conditions. Our in-house expertise and facilities are providing critical risk reduction work supporting our hydrocarbon boost demo program. Our ionic liquid propellant research started in the mid-1990s. These environmentally green propellants are high-performing replacements for the highly toxic hydrazine currently used in spacecraft thrusters, missile defense, and other systems. In 2012, NASA chose our AFM-315E monopropellant for their green propellant infusion mission. The launch opens the door for military and commercial companies to use this propellant for their systems.
2, 1.
Besides our in-house work, we work with our industry partners through the RP21 program to deliver advanced propulsion technologies. We also work with other AFRL technical directorates to deliver integrated, revolutionary capabilities to the warfighter and address current warfighter needs. We develop advanced solid rocket propulsion technologies supporting the sustainment of the Minuteman III and future ICBMs. Our aging and surveillance technologies make it possible to assess the health of the individual ICBM motors, which will save billions over the life of the Minuteman fleet. Since 2000, we have transitioned over 79 solid rocket technologies supporting the Air Force Nuclear Weapons Center, NASA, and commercial companies. Leveraging the success of the recent X-51 hypersonic missile test, the DoD is developing the technologies for a future long-range strike weapon capable of flying 600 nautical miles in 10 minutes. We are leveraging our solid rocket technologies to develop a booster concept that can get the hypersonic front end up to speed and on its way. In 1994, Lockheed Martin proposed using the Russian RD-180 engine for the Atlas V launch vehicle because of its low cost and high efficiency. The last large hydrocarbon fueled engine, based on AFRL technologies made in the U.S., was for the Apollo program's Saturn V. The oxygen-rich stage combustion cycle of the RD-180 engine is about 30% more efficient than the gas generator cycle used on the Saturn V. And the U.S. has no industrial base experience with this cycle. In 2007, AFRL started the Hydrocarbon Boost demo, which is developing the technology base in the U.S. for the oxygen-rich stage combustion cycle. We have pursued advancements in the turbopump, preburner, thrust chamber, and in materials that can survive the hot oxygen environment. We have also pursued advancements in modeling combustion stability in hydrocarbon-fueled rocket engines. Combustion instabilities can be catastrophic, as we learned during the development of the engine for the Saturn V. We conducted over 2,000 full-scale tests to finally resolve the combustion issues with the engine. We can't afford to do that today. The Hydrocarbon Boost program is the basis for the future of DoD access to space. After years of developing advanced Hall-effect thrusters, we saw the first U.S.-built thrusters fly on TACSAT-2 in 2006. They are also currently used on the advanced EHF military communications satellite. They played a vital role in 2010 when the upper stage failed during launch. The thrusters successfully maneuvered the satellite into orbit, saving the billion-dollar satellite. Hall thrusters are mature, and all of the commercial satellite makers are making all-electric satellites. Field reverse configuration, FRC thrusters, hold great promise for the next generation of spacecraft thrusters. They are less complex, lower weight, and can be used as a multi-mode thruster, operating in both chemical mode with high thrust or electric mode with high efficiency. This multi-mode thruster provides much greater on-orbit flexibility to the warfighter. Finally, our systems analysis capability allows us to show the incredible payoffs that are possible using our technologies. The group is so good that they are often called upon by OSD, Strategic Command, and other customers to conduct analysis and to support analysis of alternatives. Their work directly influences future acquisition decisions across the Department of Defense. Our facilities really are a national asset. They support not only our own research, but are also used to support numerous operational and developmental systems like the motor production for the Standard Missile, Atlas V strap-on booster, and the super stripey Nano satellite launcher. Since 2000, we have seen our technologies applied over 164 times to both military and commercial systems, and have supported over 20 space and missile systems. In a word, we are rocket propulsion technology.